right.
All right, so this is a torque lab, and in the beginning, we start with hanging a 100-gram mass and a 200-gram mass on either side. So this is part one. And this is like an introduction for the students to come up with a, they're trying to come up with a rule for torque. And so we're using rubber bands here because they don't have any mass really compared to the 100 grams and 200 grams. And so what students do is they will put the rubber bands on each side, and they'll place a 50, the 100-gram mass here, and then they'll find where they need to put the 200-gram mass in order to balance it, and they'll see that if I put this at like 30, and this one on this side needs to be at 15 to balance out. I don't even know if I have it at 15. Or it's actually not even at 15, it's at 15 centimeters away. Ten, 11, 12, 13, 14, 15, and that's, I think, close to 30. So this is pretty close to balancing, but they'll move it back and forth until it actually does balance. Okay, so it does balance right there. And so they might have to move it around a little bit, but they hopefully will see twice the mass is half the distance. And what a torque really is torque is equal to force times lever arm distance. And the lever arm distance is always measured from the pivot point to the mass, or to the force. So this is a lever arm distance here, which ends up being 30 centimeters. And over here we have a lever arm distance of 15 centimeters. Here we have now we're supposed to do this in Newton, so this would be a 1 Newton force times 0.3 meters, gives you 0.3 Newton meters, which is the torque. And on this side we have 0.15 meters, and this is 2 newtons, and so if you do force on this side times lever arm distance, you get 0.3 Newton meters. So force times lever arm distance equals this force times lever arm distance, and that means that this system is in equilibrium. If it was out of equilibrium, the torques were unbalanced, you would actually have angular acceleration. Just like if forces were unbalanced, you'd have linear acceleration. Here you would have angular acceleration if the forces are unbalanced, or if the torques are unbalanced. And we're not going to get into that part of this. We're actually, the only torque I have us doing, we're not getting into angular acceleration, because if we were to do that, we probably, that's more of a chapter 8 thing. Angular acceleration, you know how like angular velocity was chapter 8, I was saying, but we used it in chapter 5. Angular acceleration is a chapter 8 thing. But we're using, we're studying torque at this point because we study circular motion. And if you want something to move in a circle, you have to apply a torque to it to make it start moving in a circle. If it's at rest, you have to apply a torque, a force times the lever arm distance. Just like if you have a mass that's sitting there and you want to get to start moving forward, you'd have to apply a force to it. Here we're applying a torque to something to make it move in a circle. Okay, does that seem all right?
Yeah.
That's what torque is. Okay. So that's what part 1 is, and so I'm thinking then we'll have like a discussion about it with them, and I'll just do it on the whiteboard over here, so I'll just move my camera, I guess, to be like this. And of course I need so the variable for torque is tau. And it's force times lever arm distance. I don't know if you can see that. Let me get some darker. Torque equals force times lever arm distance.
I can take a picture of what you
Okay,
want.
all right. And what we have here is we have this, what we just did was we have this pivot point right here, and we had a force 15 centimeters away, or 0.15 meters. That's our L value, that's our lever arm distance. And our force over on this, oh, and our force was 2 newtons. And on this side, we had a lever arm distance of 0.3 meters, or 30 centimeters. And this force was 1 newton. So when you did force times lever arm distance on one side equals force times lever arm distance on the other side, that means the torques on one side equal the torques on the other side. They're equal and opposite, so that this will be balanced. So you have force times lever arm distance 1 equals force times lever arm distance 2. And 1 Newton times 0.3 meters equals 2 newtons times 0.15 meters. And so they're equal. We have 0.3 Newton meters equals 0.3 Newton meters. So that means the torques are balanced. That means this thing is balanced. It's not moving. And they're going to use this idea all the way throughout the lab. This is the main idea. And so the next thing they do is, this is part 2, and so that was part 1, and then after part 1 I think I'm going to have this discussion of what torque is. Part 2, we add the mass. Actually I do a problem. At the end of part 1 I have students try a problem. I say, okay, I introduce this to them, and then I have them do a practice problem where they have people on a seesaw, and the seesaw is 4 meters long, and there's a person on one end that has a mass of 100 kilograms, and then there's an 80 kilogram person over here, and I need to know where to place the 80 kilogram person so it's balanced. So I know that this is mass 1, so I know my lever arm distance 1 equals 2 meters. And I want to solve for lever arm distance 2. I want to know where to put that person so that we're in equilibrium. And so what the student should do is say, okay, torque 1 equals torque 2. Now, it officially is force times lever arm distance, but you can just do mass times lever arm distance because the g's actually cancel. Like, this force is m times g. This force here is m times g. The g's cancel, so we literally can just do masses on both sides. I don't know how you feel about that. You want to just stick with force, or you want to stick with masses?
I feel like I would rather stick with the force of gravity, just because there's still weird about calculating that.
Okay, good. So let's practice that. Okay, so let's just stick with that. So force 1, lever arm distance 1 equals force 2, lever arm distance 2. So this person here is m times g 1 times lever arm distance 1 equals, m times, and so m2 g lever arm distance 2. And so now we just plug in our values and solve for L2. M2 is 80 kilograms times 9.8, and L2 so, oh shoot, wait, this is not going to work. Did I say the 80 kilogram? I need to fix that. In that practice problem, did I say the 100 kilogram person's out at the end?
Yeah, well, oh, is that in, so did you put it at the,
Yeah, it's under part 1 of the lab.
oh, I didn't even see, okay. Yeah, so the 100 kilogram person is at the end.
I need to make it the 80 kilograms.
Okay.
So there's a mistake right there. And so this side would be 100 kilograms. So I need to fix that.
Okay.
This person here is 100. This person here is 80. Okay. So this L2, I think, comes out to be 1.6, if I'm not mistaken. Yeah. So L2 is 1.6 meters from the pivot point. So from the pivot point, this is 1.6 meters. Okay?
Okay.
So then in part 2, we go back to the lab. And we say, I forget what part 2 says.
Part 2 is, it starts with what's the equation for torque when given the applied force and lever arm distance. And then, so they'll have to use the mass hangers to hang masses from the meter stick and calculate positions of the masses. So if you were, so make sure the meter stick is balanced. And if you were to place a 50-gram mass and hanger 40 centimeters from the fulcrum on one side.
So I'm having them now use the hanger. So the mass of a hanger, just to let you know, is 15 grams.
Okay.
0.015 kilograms. And they're going to take, so that has to be part of the equation now. And I'll put the 50-gram mass 40 centimeters away. 10, 20, 30, 40. Oh, by the way, when they're calculating distances, they should look right on the edge here. See how the pivot point's right there? The pivot? Or this little wing thing here?
Mm-hmm.
That line right there is where the center of mass of the system is. That line is where they need to measure to. Okay, that line right there. So I have that right on the, for me it's 40 centimeters away. It's over on the 10 centimeter mark. If I put it on the other side, it would just be on the 90 centimeter mark. And then what do I forget if I do 100,
The other one is, so it says to calculate where the 200 gram.
where the 200 grams is going to go. And I got to put in there, I didn't put that in there, that I don't want it to be trial and error. I want them to calculate it.
Okay.
And so I need to add trial and error. No trial and error. You know, you have to calculate it. I'm just going to put it on for now, just to show here where it goes. And so they're going to do the exact same equation. They're going to do the exact same thing as we just did with the 2 people, but with the mass hangers.
Okay.
And it might seem a little redundant, but it's okay. I want them to do another practice problem. And I want them to do it with hangers.
Mm-hmm.
So I wanted them to do this, and then now we're adding a new piece to the puzzle is with hangers so that they can make sure they understand how to do that. Now, you took a picture of that, right?
Yeah.
Okay, so what we're going to do now is do that calculation the exact same way we just did these other 2. And so really all I have to do, I can just erase this right here. But like I said, the one difference here is that they now have hangers that are 15 grams. So our mass on one side is 50 grams plus 15 grams. So it's 65 grams over here on one side. It's not a person anymore, it's a mass hanging down. And so it's 0.065 kilograms times 9.8 newtons per kilogram. That lever arm distance is 0.4 meters, because we said we're going to be 40 centimeters away, equals, we put 200 grams on the other side, so that's 215, because you have to add the mass hanger. So it's 0.215 kilograms times 9.8 newtons per kilogram. And we're going to solve for that lever arm distance, that L2. Ooh, if I stop it, is there a way of pausing it so then you can restart it? I don't know if there's...
I don't know if you can pause it.
Yeah. So we can do this calculation. I don't have a
Do you want me to do it?
Yeah.
Um, 0.12. That sound right?
Yeah, let's see, yeah, that looks pretty good. So we're at 0.1. I think we're at, oh man, where did I put my glasses? Oh, there they are. So it worked out well. Actually, yeah, it's 0.12. I got 0.125 maybe.
Okay, this is 0.121.
0.121, so close enough. And this, the 50 centimeter mark actually, so if you look closely at this, this thing here, if you look at it, you'll see that it's not at 50 centimeters. See how the pivot point there is like 50.5?
Oh, okay. It's off center.
So it's off center because that meter stick is not homogeneous or whatever. It's not printed correctly, whatever. So it's going to be off a little bit.
Okay.
I really don't want to get into, maybe some students will notice that. They probably will. So really, in reality, it's 0.12 meters from that spot over,
Okay.
which is really close to that. Okay? All right, so part 3. Now we're going to add a little twist-a-roo here. We're going to, and so, yeah, so now they go ahead and check it. The next thing is, in part 3, or actually, is this part B? This is, did I call it part 3 or did I call it the part B of part 2?
There is a part B with a 50 gram mass moved to the 20 centimeter position.
Yeah. So this goes to the 20 centimeter position. Or not 20 centimeter position, but 20 centimeters lever arm distance. And if I did this right, I really should move it in a little bit like that. And then I think I want to do the 100 grams, right? I need to put 100 grams somewhere.
Yeah, and then the 100 gram mass goes to the 40 centimeter position.
So I put this out here. And then I have to now calculate where the 200 gram mass goes. Have it be in equilibrium. Look at that, that's fun. Okay, look at that. Nice. So, what happens here is it's the exact same idea, except now you have,
You're on it.
now we're going to have this is our pivot point in the middle still. Plus 1, 2, 3, and it's balanced out. So now we do torque 1 plus torque 2 has to equal torque 3. The two torques on the left-hand side have to equal the one torque on the right-hand side. And we're going to go ahead and just do force times lever arm distance plus force times lever arm distance equals force times lever arm distance for 3, that's 2. And so this is M1G L1 plus M2G L2 equals M3G L3. Okay, so let's go ahead and just plug our values in. Our 50 gram mass, plus we have to remember plus hanger. This is where students will forget about the hanger. That's why you'll see in the lab I constantly say plus hanger, plus hanger, plus hanger.
Okay.
So this is 0.065 kilograms times 9.8 newtons per kilogram times L1, and it got moved to the 20 centimeter position, right?
Mm-hmm.
0.2 meters. Plus M2 is the 100 grams, but that's 115 grams, which is 0.115 kilograms times 9.8 newtons per kilogram. And its L2 position is 0.4 meters equals, I can erase this here, right?
Okay. I have my notes too, but I'll take a picture again. Okay.
Equals M3, which is 200 grams plus the hanger. People are going to forget this. If they go, oh, my numbers aren't right, that's the first thing to look at is the hanger. So this will be 0.215 kilograms times 9.8 newtons per kilogram times L3, and that's what we're trying to solve for. Do you want to just, do you want to calculate it, or? I guess,
Sure.
I mean, it'd be nice to know the number going into class, so.
Yeah, I can. And I can just leave out G, right? Even if I have
Leave out what?
the G.
Yeah, you can just leave out the G. You could just do 65 times 20, 115 times 40, 215, divided by 215.
Okay.
Because I've had students do this in gram centimeters instead of Newton meters, and it's fine. But you're right, we really should keep the units consistently correct.
Yeah, they're still like writing 9.8 for force and gravity, so just in case.
Yeah, this is good practice for that.
Yeah. Okay, I got 0.274.
0.27, and this says 0.276, but again, it's half a centimeter over. So that worked.
Okay.
So that's the other thing to look for. If a student says, oh, wait, I'm off a little bit, check not only that, one thing to check for is if they forgot to put hangers into the masses. The other thing to check for is if the pivot point isn't exactly on the 50 centimeters. It's like this one here is a half a centimeter off, so it shifts it shifts your values over. You have to measure from where the pivot point is, not from 50 centimeters. Okay, so what did you get for L3?
0.274.
Actually, eventually I'd like those numbers too. Maybe I could get your notes or something
Yeah.
going into class. All right, part 3 is to find the mass of the unknown, right? So
Yes.
we've been solving for lever arm distance this whole time. Now we're gonna have them solve for mass, an unknown mass. And I don't think I tell them what masses to use. I think I just tell them to put actually maybe I should say take all the masses off the bar now and place the unknown mass on the bar. Yeah, if you read it once, it's just, I forget what I wrote.
Yeah, it says use the seesaw setup to find the mass of the object with an unknown mass. And then to use a hanger. And then on the other side, use a known mass plus hanger to put the meter stick in equilibrium.
Okay, so I mean, they can do it whatever way they want, because I left it open.
Yeah, I think it's clear.
Okay, so, I'll just put the unknown mass maybe did I tell them where to put the unknown mass, or did I just say place it on one side?
No, just place it.
Okay, all right, so I'll go, how if I go 20 centimeters out? I'll make my lever arm 20 centimeters. And then, I don't know, use the 100 gram mass. It really doesn't matter. They can use 200. 50, if they use the 50, they can run into trouble because this mass, the unknown mass is 50 grams. Its hanger is 15, so it'll be 65. Actually, if they use the 50 grams, they would find it's just the same spot. So
Okay.
the 100 grams. So I don't know. And maybe I should put in there use the 100 gram mass to find it, because that's kind of, it's not cheating, but it makes it too easy. Okay, the other problem here is that this, oh shoot, carries. The other problem that we're going to run into here, so I might just change this to tell them to use the 100 gram mass to solve for this, because if they use a 50 gram mass, I think it's just going to be too easy. They don't have to do any calculation. The other thing here is that this unknown mass hits the tabletop. So one way around that is to have it hang off the side of the table. Like I could, actually what I should do is flip this around. Put it at 20 centimeters. You have it hang off the edge. Then take the 100 centimeters. And do it like that, have it hanging off the edge. Or we can take a box and set it on there. I don't know what you guys prefer.
If we, I don't know, if we have enough boxes, maybe
I think we do.
do better.
And maybe even it might even be easier just to start with with it on the box.
Yeah, because then so they don't walk and hit it. I don't know.
Yeah. So I'll put boxes underneath every one. And we set up, because it also raises it up and makes it easier to look at.
Yeah, that's true.
We'll tell them that's why we did it. We're thinking of them. All right, so in this case here, oh shoot, did you take a picture of that?
Mhm.
Nice. So in this case here, it's a very similar thing. where we have our unknown, and we have 100 grams over here. And I'll call this 1, call that 2. And we just do F1 L1 equals F2 L2, M1G L1 equals M2G L2, 0.1 kilograms times 9.8 newtons per kilogram times L1. This one we actually looked at. It's about 0.15. 1, 2, 3, 4, 5. Yeah, it's around L1 of 0.15 equals our M2. That's our unknown times 9.8 newtons per kilogram times L2, and I put L2 at 20.2 meters. And again, you can just get rid of the 9.8 and just say 10 times 15, which is 150 divided by 20. So that's 75? Ooh, that's not right.
Yeah, that's what I'm getting.
I want 65. Hold on a second. Well, in reality, this 0.2 is really 0.15.
Oh, that's when.
What is that? That makes it worse. Ugh.
Well, wait, isn't the mass of the other one? It's not 100. It's the 0.115.
Oh, that's the. That's
the opposite.
You know what? Didn't I say that's what they're gonna do? Because I did it.
Yeah, I keep forgetting. That's hard to keep track.
Yeah. I'm gonna say to the students, listen, even when we do it, we forget the hangers. Don't forget the hangers.
Okay, wait, so it's 0.115 times 0.15 meters.
Divided by 0.2.
So I'm getting 0.086.
0.086 is not.
What am I doing? 0.115 times 0.15.
0.115 times 0.15.
0.017.
Divided by 0.2.
0.086.
0.086. I want 6. We're off by 20 grams. That's a lot.
Am I doing that?
I might be doing. I might be giving you bad numbers here. Hold on. Oh, this is only. This is 100 grams. This is 115 grams, right?
Mm-hmm.
It is 0.15 away. This is the unknown, which is 0.2 minus, it's not really 0.2, it's, what is it?
So,
It's really
What's
more
it?
like,
isn't it like 10, a little over 10 centimeters away, the 100 gram?
yeah, so I have it like, so I added that little bit away there and that little bit in there
Okay.
to get 0.15. Is that right?
What is it? Or,
No, it's 0.105.
okay, okay.
I'm an idiot. Okay. Yeah, that's not, it's not 15 centimeters, it's 0.105. Okay, thank you.
Okay, let's see. Okay, so this is 0.06, is that? Okay,
Yeah.
that's right?
That's
Okay.
about right.
0.06,
It should be 0.065, but
okay,
what if I make this 0.1, this could be 0.15. Try that,
okay,
because I didn't take into account that little piece that got pushed over.
0.15. Then it comes out to 0.08, is that right?
Really? That's a
Let me
big
see.
difference. I like the 0.2 better. It's actually, it might even be more like point,
Yeah,
yeah, let's go with 0.2. 0.06 is pretty close, we're only 5 grams off.
okay.
Okay. Then, this next part is calculating the mass of the meter stick. And so, what we're gonna do now is we're gonna take the unknown mass off. And we're actually gonna take all the masses off. And I think I said move the pivot point to the 70 centimeter spot.
Yeah, yeah,
And then, so now it's unbalanced. And that's because the meter stick has a center of mass at the 50. And so at the 50, the weight of the meter stick pushes down. And so I asked them to use a 200 gram mass to balance it. Okay. And I want to use this setup to calculate the mass of the meter stick. So again, we have an unknown mass. So the setup is going to be identical to this part here. Except our fulcrum now is pushed over to here, let's say. This is the 70 centimeter mark. And this is 100 centimeters out here. 50 centimeters are right here. And this is 0 centimeters out there. And what we've done is we placed a 200 gram mass here. And it has a lever arm distance of 0.125. I'll call that L1. So we have here, if we just plug in, our mass is 0.2 kilograms. 0.125 meters is our lever arm distance. And this actually is 0.2 meters is actually the right number. Because the meter stick, what we do is we assume the meter stick is shrunk down to its center of mass at the 50 centimeter mark and assume all the force of gravity of that meter stick is at the 50 centimeter mark. Now, students are going to not like this, or they're going to be confused by the idea that they're going to want to break this up into two parts. They want to take the left-hand side and treat that like a mass trying to turn, and then they want to take the right-hand side and treat that like a mass that wants to turn. And that is valid, that's okay to do, but why do it when we can take the whole system and shrink it down right to the center of mass of that meter stick and use that as my force? This will be the mass of our stick, or meter stick. Actually, I'll do MS. So, so if we do, oh, actually this works out nice. If we do this calculation, the mass of this meter stick should be 125, it's 0.125 kilograms. So the meter sticks will probably range between 80 grams and 125 grams, or 100, I've never seen one at 150. But the older ones tend to be, you know, the newer ones tend to be like 80, the older ones tend to be about 125. That's an older one, so I'm not surprised it's around 125.
So
Does that seem okay?
where does the 20 or the 0.2 comes from? The distance of like the center, so the new, like where the fulcrum is to the center of mass.
Yeah. It's from the new, so lever arm distances are always from fulcrum to the force. And what we're doing is we're taking the weight of the meter stick and putting it at the 50 centimeter mark.
Okay. And why can you do that? Because that's where the center of mass is when it's out. So that's where the.
Yeah.
Okay.
So this is an important idea in mechanics, that you can do this. You can shrink things down to their center of mass. So some people are going to want to do this. Some people are going to want to say, and this makes a lot of sense to me. It's actually valid. It's not bad physics. But we want them to understand this idea of center of mass. So what some people are going to say is, well, why don't I just break the meter stick up into two pieces? I'll take this piece here and go to the center of it. So I'll call this like force of gravity 1. And then I'll go to the center of mass of this one, force of gravity 2 for this meter stick. And so what's happening here is this is 30 centimeters away. So this actually is a 15 centimeter distance here. And this is a 35 centimeter distance here. And you could do ratios, right? You can do a ratio of the meter stick and all that, and so it gets to be a little bit of a mess. But if you think about it, if you have these two here, these two actually can become one force at 20 centimeters. So this one force at 20 centimeters acts the same as these two forces split up separately, with this mass on this side acting this way, this mass on this side acting that way. That acts exactly the same as if you were to put the whole force, the whole weight at one spot.
Okay.
And that's really how this should be done, is that, because I know these students won't get into it, but this is the way, it actually makes things easier to work with in physics, right? If you take the center of mass of objects, that really helps out in physics. Does that concept seem okay?
Yeah.
Okay.
Yeah, I think they'll definitely have questions on it, but.
That they will. They definitely will. This is this is why I'm saving this to later, to the end.
Yeah.
Now, part 4, the last part, I've asked them to find the normal force of every part. This is part 5, right?
Yes.
So part 5, and Chris came up with this idea, so this is new for me, this kind of thing, is find out what the normal force is for each section of the lab. And so for this, what that means is there's a force right here, like this stand is holding this whole system up, right? Now that they know the weight of the meter stick, they can go back to each part and say, okay, well, what's the normal force right there at the stand? What it really is just the weight of the whole system.
Mm-hmm.
So, like, for example, this right here is 125, or is 0.125 kilograms. Oh, I screwed up. I did it again, I forgot the mass hanger.
Oh,
That weight did seem a little high to me.
I didn't even notice.
Yeah, I didn't either until just now. Because until I just talked about the hanger again. So this mass should be 0.25 because it's with the hanger. Oh my goodness, so I can't do this one in my head. The other one was easy.
Okay. 0.134. Okay. 5.
So it's heavier now.
Yeah, 0.134.
Okay. Actually, let me go test it out. Let me go mass it, because that's what I want students to do, is then go mass this
Okay.
and see if they're correct. Now, in order to do this, they have to take this off, this off. They're gonna ask you, should you take this pivot point off? And the answer is yes, because it's at the pivot point, it has nothing to do with torque. That mass that's at the pivot point, since this mass is right at the pivot point right here, this center mass, this center hanger, it's not involved in the torque calculation because its lever arm distance is 0, so it's never involved. And so what we did was we just found the mass of this meter stick, and so we're saying it's 135. Okay, feels close to that. Guess what it is?
135?
Yeah,
Oh, wow. Okay.
nice.
So that's not in there for, they don't have to find the actual mass though, right?
Of,
Of the meter stick for part?
yeah,
So for part 4, it's not,
oh, it's not in there?
no. So like part 3, there's a calculated and actual percent error. But part 4 doesn't have that.
Oh, I should put it in there. What was the actual, what was I, oh, that was for the unknown. Oh, let's do that for this too, okay, yeah, let's do that. This should have that. Cause it's kind of fun doing it, this should have that. Okay, so I'm gonna set up now for, let me go back to part 1 and just talk about the normal force.
Do you mind, so they asked about percent difference in the one,
Should be
in one
percent.
lab, so now we're doing percent error?
Yeah, that should have said percent error.
Okay,
That was a mistake.
okay.
Yeah, I don't know why, because I like using percent difference when when you're comparing two calculations and neither one's actual. I tend to say percent difference, but when I know one is the actual value, I should say percent. That's when I say percent error, and I just made a mistake with that one, because that should have been percent error.
Okay.
Okay, so what happens so I have this normal force thing, this normal force question, and what the normal force basically, all it really is going back to each part, and I'm not really going to worry about it being balanced or not now, but the normal force is just asking what's the weight of the system. And you actually have, in this normal force part, you do have to include the middle hanger, because anything that has weight is being held up by the tripod or by the support. So now that they know the mass of their meter stick, they take that plus the mass of all the hangers that are on here, plus the masses that are hanging, add those all together and then multiply by 9.8 to get their weight, and the normal force is just equal and opposite to that.
Okay.
To be technical here, if we want to be really detailed, these hangers are 15 grams with the little loop on it. This support doesn't have a little loop on it. So, I don't know how technical we wanna get, like, let me mask this.
So for the meter stick, did you keep that on?
It's actually 10 grams. What's that?
For the meter stick, when you actually took the mass of the meter stick, did you keep that part on? Or
I took it off.
Okay.
Okay, without the loop underneath, it's actually 10 grams. So,
Okay.
I don't know how specific, how much I'm gonna care. I might, if it comes up, I might bring it up, or if somebody just doesn't. I don't know, I'm gonna have to feel that one out, I think. When I see it happening, I'll
Yeah.
probably say something. But if somebody already did it, well, actually, if somebody already did it, I might say to them, did you count that middle hanger? And if you did, what mass did you give it? And if you gave it 15 grams, is this really 15 grams? You know, that kind of questioning. And
Okay.
so with the hanger, with this brace, with the hanger is 15 grams, without it's 10 grams. So that, Olivia, does that seem clear what that last step is, asking for the normal force?
Yes, so they want of the whole system. So it's just the mass of everything times 9.8,
Yeah.
really.
So actually, here's another situation where they can practice solving for force of gravity.
Yeah, that's true.
Okay. So actually, I put this together quick, but it's actually my favorite one I've put together on torque so far, because I've kind of done pieces of here and there. There might be, but that's why it might seem like there's a lot of parts. I don't know if there's a part that you think that needs to be taken out because it's too long or something, or I try to have a transition from one type of thing to another where they would get some practice also, so that's why I had more parts too. It's kind of like doing practice problems.
Yeah, I think it's good. I think that the part that will probably be the most challenging for them is part 4, finding the mass of the meter stick.
Yes.
But other than that, I feel like once they get the first part, they should be able to go through
Yes.
the other
Okay.
ones.
All right, Carrie, we're going to stop right here. And then if you have any questions, just let me know, and then we'll see. And then we're going to, we'll send you the edited version of this too, so you can look at it. Okay, see ya.
Bye, Carrie.
Did I get you?
Yep.